So the case B is when G is bigger than R. That means G by R is bigger than or equal to 1. And the constraint V less than or equal to 1 is relevant. Because what happens is the following. When G is bigger than R, it is not possible to grow the firm at the rate G. Remember, rho is, R is bigger than rho. So this firm has an ability to invest $1 and earn more than what the people want, what the stockholders want. So unless something else happens, this company will grow as much as it can. So if it is allowed to grow at rate G, it will grow at rate G. Okay? So it grows at rate G, but it cannot grow at rate G by simply keeping its earnings and without paying any dividend. Because then it can only grow at the rate R. So in order for it to grow at rate G, it has to retain all its earnings, and it also has to get some money from other stockholders, new stockholders. Okay? So that is external equity or external financing. And so what happens is that at that point, all the dividends will not be paid. No dividend will be paid. And when no dividend is paid, V becomes 1. We cannot have V bigger than 1 in order to grow faster than R, because all we can do is keep our earnings and invest it. We cannot earn more than the earnings that we have. We cannot keep more than the earnings we have. Okay, so that's why this constraint becomes relevant. Okay, so that case is very same as A1. You know, W2 is less than 0, so tau 1 we go to subcase B2. Now, when we go to subcase B2, we are not the same situation. Of course, we can show that B2 cannot be sustained more than one point in time. But why? You have to give me control. My mouse, yeah, now it's controlled. Yeah, good. So you see that where am I? So you see here, when I'm at this point, I'm going to along go this path. This path V star is G by R. But right now, when I am at point here, that V star will become 1 because G by R is no longer G by R is bigger than 1. So I cannot go V star equal to G by R. So I cannot follow this path, but I can follow a path when V star equal to 1. So my next calculation here will be different from the case A. Okay, that's what I mean by that. But it's not much different, at least at this point. But later on, it'll be one more point is coming in. Remember the picture? So I'm in case B2. B2 is this control, where V star is less than or equal to 1. Okay, if you go to the table, it's min of G by R, comma 1. And since G by R is bigger than 1, the min of that I guess is 1. Okay, I go back to the table. It's better to just go back to the table to show you. We are in this case B2, but B2, that 1 becomes 1. Because G by R is bigger than 1, so min of 1 and G by R is actually 1. Okay? I didn't want to break another row for that. So I could put A2 and a dash here and a B2 and a dash here. And then I don't need to do this min. But that's okay. As before, the singular control cannot be sustained except only can be sustained for R equal to rho, but it cannot be sustained under this assumption. And as in subcase A2, W2 is increasing at tau 1 from 0 and become positive after tau 1. Thus, at tau 1 plus, we are in subcase B3. So the singular control that happens here, this is the singular control, is now not a singular control anymore, and we are at B3, and this is V star 1. Notice now that now we want to go through, this equation is now different. Previously, that we were growing at rate G in case A3. But in case B3, we are growing at rate R because all of the retained earnings means the earnings are being done at rate R. So when I retain them, I'm going to earn R on them. So I get R minus Rx, which is negative of Rx, negative growing at rate R. And I have alpha B, which is the guess for the value at because up to I make a guess alpha B, so alpha B stays up to tau 1, and at tau 1 I still have alpha B, and I'm now at this equation, and I have a lambda circle equation, which is this equation. These are different equations than A3 equations. So lambda tau can be solved for lambda tau 1 equal to 1 by R. I can solve that equation because that equation is easy to solve now. I don't have any control in that equation, so I can solve it. And this is my equation, lambda tau. As lambda increases, W1 increases and becomes 0 at time tau 2. Because I can solve this. And so there is a tau here, and I can put this W2, which I can put W1. W1 is CR lambda minus 1. W2 is already bigger than 0. So I want this to become 0. Now this to become 0. So when this becomes 0, I have a CR times lambda, and I have the value of lambda here, and minus 1, and I set equal to 0. When I set equal to 0, that is 0, and I get tau 2 equal to tau 1 plus this quantity. And once again, now, as before, I switch to B4. And B4, okay, let's do a picture here again. So I started here. Then I was in a singular control on B2. Then I was at B3. Then I was a singular control at B4. And then eventually I will be at B5. And I will show that I can stay there forever. Okay? Remember, B6 and B8 and B7, they are not feasible anyway because these are W's that you cannot sustain. Because W1 and W2 have a related formula, there is no way we can have these conditions possible. At this point, we are at B4. We have W1 equal to 0. And we have a singular control on external equity. And we want to show whether we can maintain this or we can only keep it for one point in time. Turns out that we can again keep it only for one point in time. So we see the maintain singular control, we must have W1 equal to 0, which means W1 circle equal to 0, which means lambda 2 circle was 0. And to compute lambda circle, I have to have this. I put the value of lambda at tau 2 here, which is 1 divided by RC. And at tau 2, we have W1 tau 2 0 gives this. And we put that in 5.58. I can put that value in 5.8. And then I equate the right hand side to 0, and I get again R by rho, R equal to rho. That means that in order for me to be maintaining this, I need R equal to rho, which again we did not assume. We assume R bigger than rho. Because R equal to rho is a trivial kind of case. You earn the same amount of money the stockholder wants, so you are indifferent between putting money or not putting money. And so lambda 2 circle will become 0, bigger than 0, immediately after tau 2. And we are in case B5. And now I want to analyze B5. B5 is this case. And we have an X circle which is growing as GX and lambda circle going in this way. And this is very similar to the case that we had before in some way. So we can show that this will continue to remain. It is really almost the same as before. And we basically have come to the point where we have derived this. Once again, you see there's a mapping. We go from here to here, go from here to here, then continue in case B5, and I will reach somewhere. And that somewhere, from any alpha B, I will reach somewhere. And that somewhere is connected to that alpha B. So I can go backward and start with X0 and go to find alpha B. Okay? Or if I start with alpha B, I keep going here, I keep here, then I go here, then I go here, I come here. That will be some number of alpha B. I equate that to X0, I get alpha B. Okay? So either way, it's a one-to-one mapping between alpha B and X0. Okay? Now we want to show what is by the way, the tau 1 formula was easy to figure out. The financial meaning of that was quite easy in some sense. So if you gave it to somebody, Einstein or somebody, they can do it without control theory. This one is a little bit harder. So let's figure out what is the meaning of this in a financial sense. It's a little bit complicated, but you have to stay with me to see what's going on. We will go slowly. The firm issues $1 worth of stock. Issue means I will sell $1 worth of stock to external stockholders at time t minus tau 2. When I sell one stock, the stockholder gives me money. The new stockholder gives me money. And I also pay some money to a broker. What does a new stockholder wants back? Well, he wants back dividends, because that's all. This company is only dividend. We're not liquidating the company. We liquidate the company, its value is 0, so you don't get anything out of it at capital T. So the only way this company can distribute money to you is by giving you dividend. Okay? So when I sell a stock to an outside stockholder, I incur an obligation of pay dividend to this person. Okay? Whether there's a broker commission or not, my obligation to the stockholder, okay? And the broker's commission is something that I have to earn in order to make sure that I pay the person what the person wants, okay? So if I issue $1 of stock, I only get 1 minus C amount of money, because the C dollar goes to the broker. No, it's the other way around. I get C dollar of money, 1 minus C goes to the broker. This is because of the Krauss and Lee. I would have preferred this to be C and this to be 1 minus C, but I just keep it that way because I wrote the paper that way. I just kept it this way. Okay. Since we are attempting to find the break-even time for external equity, it is obvious that retaining all of the earnings for investment is still profitable. Okay, so what I'm trying to say is the following. I'm trying to say that if I am defining the indifference between a new stock and not a new stock, then it is clear that I will retain all of my earnings. Because I'm trying to define whether external equity, which is more expensive, whether because it's indifferent. Indifferent means I can raise it or I cannot raise it. But if I want to raise the external equity, certainly I must have done all I could do to invest my own money first, which means that all the retained earnings has to be invested. So that is important. It is very important to know that indifference point for external equity require us to conclude that the V star is going to be equal to 1 at that point. Okay. So retaining all the earnings is still profitable. And because I retain all the earnings, there is no dividend from T minus tau to T minus tau 1. That means that if I retain all the earnings, which is V star equal to 1, because remember, I'm not using control theory right now. I'm kind of using an argument in finance. That means that I will not get any dividend up to here. After that, I get all the dividend, which means that any stockholder who came here into the company will receive no dividend up to here and only will receive dividend up to here, from here to here. Since he's not going to issue any dividend, okay, all that is going on is whatever money that he gave me is growing all the way up to here. Notice what it means. If he gave me $1, he or she gave me $1, I only got 1 minus C here. Okay? But while I paid 1 minus C, the company is not giving me any dividend up to here. And the dividend comes only afterwards. But $1 of dividend requires that much amount of time. So that 1 minus C has to become $1 here. So that amount of dividend that I receive from this point to this point will give me $1. Because even though the external stockholder, I only got 1 minus C. No, I only got C dollars, not $1. I still have obligation of $1 to this external stockholder. And the only way I can meet this obligation of $1 is to earn that extra money to pay for that commission to the broker. And this means that that C dollar will become $1 here. Because I only got C dollar. I should earn money on that C dollar to become $1 here. Okay. So that's kind of the argument that you should know. So see what's going on. So this investment of C dollar grows into this amount of money at tau 1 because it is earning at the rate R. So this is the initial value of C dollar at time tau 2 and is earning the rate R. So it's earning R and it's earning tau 2 minus tau 1 amount of time. That means it is earning the rate R from here to here. And if it's earning rate R from to here, then that is the value at this point, and that value should be equal to what? What is going on here? Yeah. Okay. From the point of view of the buyer of the stock at time t minus tau 2, since no dividend is paid until time t minus tau 1, the stockholder, or somebody ask a question here? I see somebody, KS. Are you going to ask a question right now? Hello? Okay, sorry. So buyer of the stock time to, since no dividend is paid, since the stockholders' required rate of return is rho, the firm's future dividend obligation at time t minus tau 1 is e to the rho times tau minus tau 1 in terms of t minus tau $1. But then we should have e to the rho t minus tau 1 is exactly equal to that. Okay. Moreover, the firm is marginally indifferent between investing any costless return earnings or paying it all out as dividend. This also means that the firm will be indifferent between having the new available capital of this amount of dollars at time t minus tau 1 as a result of issuing a dollar's worth of stock at time t minus tau 2 or not having it. Thus, Thus, we can conclude that the firm is indifferent between issuing $1 worth of stock at t minus 2 and not issuing it. This means that before time t minus tau 2, it pays to issue stock as large a rate as possible, and after time t minus tau, it doesn't pay to issue any inch of stock. We have now concluded that all earnings must be retained from time t minus tau to t minus tau 1. Because R is bigger than rho, it follows that the excess return on the proceeds C from the new stock issue is that amount minus that amount. And that amount, when discounted this amount back to time t minus tau, we can use to show that that times that equal to 1 minus C. So 1 minus C is going to the broker. So you can see the excess earning that we need to earn during this time actually goes to the broker. So this excess return from T minus tau 2 recovers precisely the flotation cost. Okay? Is that clear now? So now we get to what's called the infinite horizon problem. And both of those remarks that I made you in case A are important now. So in the optimal control setting, the infinite horizon course, I slow down because somebody's working upstairs and I hear some things saying, don't speak too loud because they can hear me upstairs. My daughter is working upstairs. Okay. For infinite horizon case, the transversality condition must be changed to this. The condition may no longer be necessary condition. We know that because it is a sufficient condition for optimality. So a common method of solving the infinite problem is to take the limit as t goes to infinity of the finite horizon solution. This is where I want to give you some ideas of what's going on, some issues that come. So the way you solve infinite horizon problem is to solve a finite horizon problem, and then you take a limit of that finite horizon solution, and then you show that the limit actually gives you the solution of the infinite horizon problem. It's not just enough to take the limit, but you also have to show that the limit solves the infinite horizon problem. So let's see what happens in case A. So case A, G is less than R. And we consider first the case rho bigger than G. because there were two cases in case A, remember, and when we analyze that, subcases. Examine the solution in forward time from 5.5 to 5.8. So what we have those equations. So what we are doing now, if you look at this, what we are doing now, you're taking the limit as t goes to infinity of these equations. We have a solution of these here. So we can let t go to infinity. So if t goes to infinity here, this becomes infinity, right? Because tau 1 has no meaning anymore. There's nothing called infinity minus tau 1. Infinity minus tau 1 is still infinity, right? So this is 0 to infinity, and that's your solution. See, this is the only solution. This solution disappears because when t is infinity, there is nothing here. That one's gone. That one's gone. So what we are now saying is when t is infinity, the optimal solution, this one disappears. The optimal solution is like this. Just keep going. That's what we're saying now. Okay. That's the limit of that solution. So now with the limit of solution, we already got the limit of that. What about the limit of this? We're going to get the limit of that, and we will then talk about that part. Okay, so let's go back to our limit. Okay, so firm is growing at this rate. The limit of lambda t in this case becomes lambda bar. We already know that before. And we also know that W2, which was W2, which goes to asymptotically WT, which is now for t bigger than 0, is given by this formula, r lambda bar minus 1. This because okay, so that means that subcase A3 is good for all time from t equal to 0 all the way to infinity. And the maximum principle, now we can show that the maximum principle holds. Because this says lambda t is lambda bar, which means this condition is satisfied. Okay, so this condition is satisfied, but I want to mention to you that this one has a meaning in finance. Finance says the following. If you take the dividend, so if you take the dividend is 1 minus g divided by r. And this dividend is growing at the rate g and being discounted at rate r. So if you have a geometric series that's growing at g and discounted by rho and grow at g, then the present value of such a growing stream is given by that divided by rho minus g. Because g, so you can sum the geometric series and you get this. This is what is called the Gordon's formula in finance. Okay? The Gordon's formula in finance was put forward by Myron Gordon. Myron Gordon was a colleague of mine at University of Toronto. He was a one time a professor in Rochester, and then he became a president of American Finance Association. So he was an academic guy, and then he moved to Toronto because he did not like the political views in the United States, so he decided to go to Canada. So he finished his PhD at Harvard in finance in probably in late around 1950 maybe, and his thesis developed this Gordon formula. Gordon did not know that much mathematics like we do now, and finance in those days were simple. He was able to sum the geometric series at least like that. So that the geometric series gives this formula, and it's well-known formula called Gordon's formula. If you maybe you can look in the internet and you'll find out a little bit more about it. It was Gordon that once told me that he now has to teach a course that uses stochastic control, a paper by Merton, and he doesn't know this kind of math, and so I should take his finance class. So I was teaching his PhD finance class for that particular paper. And when I read that paper, I learned more about that particular problem. And I found some mistakes in that paper. And I wrote a few papers um, called Portfolio Consumption Problem. Eventually, I wrote a book on the topic. And some of my finance work is quite well known in the field of portfolio consumption problem. But I learned that because Gordon asked me to teach a course in his class because he did not know what to do. So that's a little bit of a story here of formula and my interaction with Gordon. He's died a few years ago. Now what happens when rho is less than g? Well, when rho is less than g, we know that lambda t, 5.8 lambda t grows all the way to, it keeps growing. And not only keeps growing, it actually doesn't satisfy this condition, this limiting condition. This doesn't satisfy this condition. So in some sense, it is kind of not a well-defined problem, because what happens is every solution where you give some dividend. So some dividend, which is 0 less than v less than 1, which allows you to grow the company at some rate between rho and g, will give you infinity for the objective function. That means there are many solutions that will all give you infinity. And so there is not much of a distinction between what is an optimal solution and because almost every solution is infinity. You give a little bit of dividend, doesn't matter. You give just a small portion of dividend. This v could be as small as possible as long as it's not 0. It could be 0.000001. It could be 10 to the minus 30. Because it's going to infinity, 10 to the minus 30 times infinity will still become infinity. And so this becomes a case where it's not a control theory, well-defined control theory problem anymore. And so we don't have to, we can do very good. This company is fantastic, but it is not something that we consider to be an interesting problem in mathematical sense. Okay. What happened in case B? Case B is a kind of interesting solution. So let's go why it is an interesting solution. So what happens in case B? When t goes to infinity, this disappears and this depreciates, because t minus tau 1 is also infinity and t minus tau 2 also will become infinity. So these two disappears. So the limit of the solution is simply this solution. It just keeps going like this. This is the limit of the solution. Okay? If this is the limit of the solution, can anybody tell me what's happening? Remember, nobody is paying dividend. Dividend will never be paid in this company. The company is just growing and growing and growing, and nobody's getting a dividend. So the value of the company, if you talk about the dividend, is there is no dividend, right? Let's see what is going on. One more thing here. Yeah. And so you see, and if you take 1 minus u minus v, the integral, that will already become 0 or even less than 0, right? So what happens is this. So if you look at all the way, the objective function of the problem, you see v is 1, right? because nobody paying any dividend. So 1 minus v is already 0, and then there's external equity. So this firm, the limit solution is a solution in which nobody is getting any dividend. So what I'm trying to say is that even though I took a limit of the solution, a finite horizon solution, the limit of the optimal finite horizon solution is the worst solution that you can get. Absolutely not optimal, but worse than optimal, worse than any solution you can get. So I did not know this, but Thompson and I, my advisor, when we were writing this, we wrote the following: since the firm becomes an infinite sink for investment, and the stockholders never collect any dividend, we wrote the limiting solution is a Pessimal solution because the value of the objective function associated with it is actually it's not 0. I think I should change that. It should actually not 0. It is negative. Oh, no. If you take the integral of the finite solution, it might become 0. I should do that. I should find out what the integral of the solution is and look at that. It could be okay. Regardless, 0 or infinity, I should check that just to make sure that we got it right. So we got this Pessimal solution, which is, so the optimal is, what we mean by optimal is maximize when the problem is maximization and minimize when the problem is minimization. That's called optimal. Pessimal is get a minimum solution when you want to maximize and get a maximum solution when you want to minimize, the opposite of optimal. So we thought we coined a new word, but apparently Pessimal exists in the literature. There are something algorithm called Pessimal algorithms, and so we did not coin a new word, but our meaning is somewhat different than the meaning of the word that exists in the literature. Anyway, so that's what we say here. So the only way this problem makes sense in an optimal control sense is like this. If I give you 0 to t this plus some value of the salvage value x capital T. So I can say e to the minus rho t x capital T is the value of this firm. Okay. Then what happens is this goes to 0, but that goes to infinity. So everything is fine because now the objective function is being maximized. So without some salvage value, so I would have a limiting salvage value, but limiting salvage value mathematically makes sense. It basically means that at infinity, the company will be liquidated, although infinity never comes. But in limit, the company will be liquidated, and a stockholder, if they all live to infinity, will get the share of the company, okay? And the liquidation value of the company. So that's what that means. So in order for us to kind of specify what we mean by that mathematically is something like this. So here we go. So let ut star vt star denote the optimal solution of the finite horizon problem. And let u infinity star v infinity star denote any optimal control for the infinite problem in case B. We already know that j u infinity star v infinity star is infinity because we can make that company grow to infinity without any doubt. We can simply not have external equity, just grow the company at rate g all the way to infinity. So there are many ways to do that. So we can find such a solution. Now define an infinite horizon control u infinity v infinity by taking the limit of these guys. So U infinity, V infinity is the lim of this UT star, VT star. Now what happens? This is our solution of the limit. This is our optimal solution. So the limit T infinity J UT star VT star is infinity. But J of limit, which is this one, is 0. That's what we had in our problem. We took the limit of the solution, and that limit of the solution, when you put an integral, its value is 0. Okay? So U infinity, V infinity, which is the limit of that solution, in that particular case is not optimal for infinite horizon problem. Okay? So we can sort of say that JUV regarded as a mapping is not a closed mapping. I don't want to go beyond that. It's a graph theory kind of topology argument here, but there is something called a closed mapping or open mapping. And if the mapping is not closed, then this limit and this limit are not equal. That means the limit of the function and the function of the limit, they are not equal. So this is the limit of the function, this is the function of the limit, and they are not equal. See, here is infinity, here is 0. So that's all on this first case. Now let's introduce the salvage value. If I introduce a salvage value, then J of B U V with the salvage value B, which is salvage value is given by here, is this if t less than infinity, and it is this when t equal to infinity, where I take the limit of the salvage value when t equal to infinity. Now the mapping becomes closed mapping, because now if you take the limit as t goes to infinity, this is also infinity, because this becomes infinity via this region. And if you take the function of the limit, it's also infinity. Because if you include that, this becomes 0, but this becomes infinity. So the modified model, when you have a salvage value, even though such infinite horizon problem require a salvage value as a limit. So we will not have any of the problems, because usually when we do infinite horizon problem, we're going to say that there's no salvage value, because at infinity, there's no infinity. You don't have it. There's no such time called infinity, so there's no salvage value. There's only a limit of it. But mathematically, if you want to have a theory of infinite horizon problems, you need to deal with these kind of issues. Let's put it this way. So now let's solve a problem. X0 is $1,000 a month. T is 60 months. R is 15%, rho is 10%, so R is bigger than rho. G is 5%, so R is bigger than actually G also, so we are in case A. And C equal to 0.98, which means 2% is the broker's commission. So every dollar we raise, we get 98 cents. Since G is less than R, the problem is case A, and tau 1 in this case is exactly 11 months. Not exactly, but approximately 11 months. 10 log 3 is 11 months. The optimal solution for this problem is U star equal to 0, V star is 1/3 up to 49, and U star 0, V star equal to 0 after 49. Okay, so this is the solution that we get for this problem. Optimal trajectory is xt up is growing at 5% up to 49. Then it stays exactly at that value, which is 49 times 0.05 is 2.45, so it stays exactly that value. The objective function value is 0 to 49 gives you this, 49 to 60 gives you this, and we have this value. Notice, in this case, infinite horizon problem makes sense. The limit makes sense. So we take the limit, since this is G less than rho, G is less than R, you'll see these conditions in there. The optimal control is forever this. And if I take the limit of 0 to infinity forever, like this, I get 13,333 1/3 instead of this. So you can see that company, if it's a 60 period company, okay, if it's a 60-month company, its value is 12,578. But if it is an infinite horizon company, its value is 13,330. So not much more, because the value beyond 60 is not that much because of the 10% discount rate. Okay. Oh, by the way, this is important to note, because just a second. This is a very high discount rate. This is a very high earning rate. I think this is something I did not pay attention to it, but that's okay. This is a monthly earning rate. This is a monthly discount rate. So usually the discount rate is 10% discount rate is more like a yearly discount rate, not a monthly discount rate. But as you can see here, the unit of time is month, and so maybe in the next edition I will change it to. But if you do 15 by 12, that you have to divide by approximately by 12 to give you a monthly discount rate, which is okay. You can solve the problem with a monthly discount rate around, this would be 0.01 or approximately like that, and this will be 0.015. I can divide by 10 instead of 12, and then get that as a monthly discount rate and resolve this problem, which is possible to do. Okay, but it doesn't matter. Mathematically, this is still an example. It's just a very high rates of R and rho and G. Okay. Um, Question, because I'm done with chapter 5, and I will start going to chapter 6. But if there are any question right now on any of the chapters from all the way from 0 to 1 to 5, please speak up. We have the slides. We can go back to those slides and talk about them. Any question? You guys are extremely quiet. I miss in-person classes, because in-person classes I'm able to interact more with each of the students and have them speak up more. Oh, it seems like Muhammad has a question, right?
Yeah, no, it's not a question, Professor. You're right. We are quiet today because we had another class before your class, so it seems that the students are a little bit tired, but we're still here. We're good.
You what?
We are still here. We're good. We had another class before your class, so I think we are a little bit tired, but we're
Oh,
good. Yeah.
okay.
Sorry,
So,
sorry for this.
oh, but that's only for Monday. But what about Thursday classes?
Oh, we are again silent in that classes?
On Thursday, do you also have another class before Thursday class?
No, no,
Yeah?
no.
Oh, so on Thursday you are not so tired, right?
Yes.
Okay, so on Thursday you will speak up, right?
Maybe, yeah.
Okay. Well, in case if you're tired, we can actually not do the chapter 6 right now. We can conclude the class right now. Would that be okay then? I'm okay either way.
I personally would agree because I do have a doctor appointment, but it depends on the other students'
Ah,
decision, by the way.
other students, should we continue to 6, or we should just? And also, one of the student is absent, right?
Yes, Hong Zhang, I think. No, no, sorry. Hong Zhang is here. Somebody else. Yi Hong Liu. Yeah.
Yeah, one other person. Is it Hong Zhang who's not here?
No,
No,
Hong is
no,
here.
I'm
It's
here.
Liu Yu Hong.
Yeah, my bad.
Okay. Okay. So, I think it's best now to do the chapter 6 then next Thursday, because one person is missing and one person has a doctor's appointment and everybody's tired because they had a class before. So why don't we finish this class right now, and then we will see you. Um, please read chapter 6, because chapter 6 is um, quite big chapter, and it uses chapter 4. It uses the state constraint. I just want to talk a little bit about chapter 6. even though I don't want to get into that. In chapter 6, we are going to develop a concept of what is called forecast horizon. Yeah, okay, that's good to have it. Uh, Forecast horizon is the idea that I have a forecast from, let's say, here to maybe 5 years, and I have to decide what I should do in the first month or the first period. Let's say it's a month period, so I have a forecast up to 60 months. So I have to decide what to do in the first month. But the forecast is only up to 60 months. What if the forecast I have is up to 80 months? And if I have a forecast to 80 months, then this 1 month solution may be different for that problem than the 1 month solution for the 60 month. And that is not very good because forecast after 60 months, the company will still be around and it will still be in business. So what we solve the problem for 60 months may not be optimal for the problem for 80 months or 90 months or 100 months. So I developed some ideas, and also there were ideas in the inventory theory earlier than some of the papers that I wrote, and they used to call it planning and horizon, but I changed the terminology from planning to forecast horizon, and that terminology now is standard in the literature. But what I'm saying is that if I can find a forecast to a long enough period and show that if I solve the problem for that long enough period, then my first month solution will be optimal for any problem which is bigger than that long enough period, and for any forecast that I can attack after 60 months, after that particular time. Then that particular time is called forecast horizon. And in continuous time, I were able to develop this forecast horizon in a problem called wheat trading problem. So there is a wheat trading model where I buy and sell wheat, and there's a forecast is the price of wheat. Everything is deterministic. So price of wheat is a deterministic forecast. But in that deterministic forecast, I buy low, sell high, but what are the situations where my forecast allows me to find a solution so that the solution is good for a long problem and also for any arbitrary forecast. So that apparently I use control theory to find this forecast horizon. And in order to do that, I need state constraints. And so we need chapter 4 in chapter 6. And some of the problems are problem with require a lot of cases and so it is something that it is a lot easier to follow if you read the chapter. Let me just show you. Can you give me a control, Kusali? Yeah.
Yes, Professor.
Yeah, I'm trying to do, but I don't have a control yet. So, so the first problem is a problem that I published in Management Science with my advisor. This is a, oh, what happened here?
Sorry. I was trying to give you control, but it zoomed in.
Okay. So this is something which is a straightforward optimal control problem with certain things that we call it's, but then beyond that, I give you this V trading model, and you will see something. I just want to give you one idea. The problem required many intervals and different solutions in many intervals, and of course we have a mu's and lambdas and nu's and all that because of the state constraint. So it is quite a few things. So what is going on here, for example, is that I have a solution here called decision horizon, and I have a forecast up to, oh, let's see, what do we do here? I just want to give you what is going on here. Okay, so I solve the problem for period 4, and I find a solution up to here. And then my price forecast is given by this and this. This is my price forecast. And this is a control problem. It's a control problem of chapter 4, state constraint. I can solve the problem. So my optimal solution is given by this formula and then given by this, and then this. And there's a jump here. As you can see, there's a jump. That's a lambda. So there's a jump, okay? And the solution is sell, do nothing, buy, do nothing. So this is, from 0 to 1, I only sell. That's the optimal solution. Now what I do is I resolve a bigger problem first. So let's go to a bigger problem. So what I do in a bigger problem is I go to, oh, I'm sorry. I show you here that the forecast, if I get the forecast up to 17.6, then any other problem with any arbitrary forecast will still give me the optimal solution in cell in the period 0 to 1. That means that optimal solution will remain. So then I show here a solution where my price forecast is given by this, given by this. So up to 17.6, I have the same forecast. Then I change the forecast. Okay, I have a new problem. A new problem, I have this lambda, and then a big jump in this lambda. So the jump can go up and down because of this price, but the decision in the decision in the 0 to 1 is still sell. That means I can start this decision sell, and then it will still be optimal for no matter how long the problem is. So that's done by control theory. And then I have another problem where I have different forecasts. Okay, a different forecast, but you can see the decision still sell. The decisions here change. These change, but that one doesn't change. So I call decision horizon and a forecast horizon. So that's kind of the idea, and I will go through that idea in detail on those problems. But please read very carefully because there's just a lot of things going on: lambda, mu, jump, all of these things. Okay.